All right, guys, welcome back to your favorite Calc 1 class. We're going to take a look at continuity. Okay, so what does continuous mean? What I like to remember is if a function is continuous, that means there's no holes, no gaps, and no jumps. So if you remember from your pre-calc days, they probably told you you have to be able to draw your function without lifting your pencil. That means it's continuous, right? Can't lift your pencil. So let's look at this, though, formally in this course. So continuity at x equaling c occurs if all three of the following are true. F of c is defined. That means there's no holes. It's got to be defined. So you cannot have, oops. Gosh dang it. Come on. You cannot have this going on, right? Obviously, you'd have to lift your pencil to draw that hole, right? So no, the f of c's got to be defined, right? That's number one. Number two, now that we have a little background in limits, the limit as x approaches c must exist. So number two, the limit must exist. That means you can't have any gaps. So no gaps. For example, this would be a gap, right? We know the limit does not exist there, right? So the limit's got to exist. So number one, f of c's got to be defined, so no holes. Number two, the limit's got to exist, so no gaps, right? And finally, the limit as x approaches c must equal the functional value at c, f of c. So for this third one, the limit and the functional value must be the same, so there's no jumps either. So here's an example. I cannot have a jump. Here's an example of a jump at C. That cannot occur, right? I can't have the limit being different than the functional value. So again, no jumps. So no holes, no gaps, no jumps. That's the name of the game with continuity. Okay, and then we have two terms for two types of discontinuities. Number one, a removable discontinuity. A removable discontinuity is just a hole. So this is an example. You see the picture down here. See how you got that hole, and it's different from the functional value there, right? So we got the little jump there. If you can plug it in, that's removable, right? I could easily, if I put the functional value back into the hole, now it's continuous, right? So that's a removable discontinuity. I can easily plug the hole and now it's continuous. Number two picture, a non-removable discontinuity over here. That's where you can't, right? You've got that gap there. There's no way that you can make that graph be connected, right? You can't just plug it in and now it's continuous and I can draw it without lifting my pencil. You see the problem there? So again, that's a non-removable discontinuity. No way to fix it. No way to fix it and connect it. All right, so let's look at the graph here. Where are we, part A, where are we discontinuous? I'm noticing on the graph we're discontinuous. In other words, where do I have to lift my pencil? -2, discontinuous. Notice the vertical asymptote. 0, I'm discontinuous. Notice the gap there. 2, I'm discontinuous. Notice the hole. And finally, at 4, where my limited well, it's discontinuous. Also, I have a vertical asymptote there and a functional value that's different as well. Right? So all those spots. Now let's look at each one of those one by one. At -2, is this a removable or non-removable discontinuity? Can I just plug a hole there? No, I've got this vertical asymptote. There's no way I can make that continuous. This is non-removable. All right. How about at 0? Can I just plug a hole there and make it continuous? Nope, I got a gap again. So that's non-removable. How about at 2? Yeah, 2 that's a removable one. I can just fill that in, right? I got a hole. If I have a hole, that's a removable discontinuity. I could just fill the hole. So that's a removable discontinuity. That one I could fill and make continuous. And finally, how about at x being 4? Another non-removable, right? I've got a vertical asymptote. There's no way to just fill that in and make it continuous there. So if I'm looking at this example here, it says describe the set of x values where the function is continuous using interval notation. We've got a square root function, right? So essentially it's asking us, where is this thing defined? You know, the original parent graph of the square root of x is continuous anytime x is greater than or equal to 0, right? We can't take a square root of a negative number, can we? We can only take a square root of 0 or bigger, right? So that would be where that is continuous. So what about this one? So the radicand, stuff underneath, has got to be greater than or equal to 0, right? So we add 35 to both sides, divide by 6, both sides a positive number, so I don't need to change the sense of the inequality or anything when I divide by +6. So looks like this is where this is going to be continuous, right? But we want to use interval notation. So from 35/6 on is where that will be, you know, about right here and on, right? All right, let's look at the next one. Where is this one? Continuous. 1 over x squared plus 1. Now, what I'm looking at with a rational function, is there any problems? Is there any values of x that makes me divide by 0? Like, I can't divide by 0, right? My denominator cannot be 0. But if I'm looking at x squared plus 1, even if I put in like negative numbers, x is being squared, right? So it'll always be positive. So this is a positive value, and then I'm adding 1. This will always be positive on the bottom. There's no x values that'll make me divide by 0 on this. So this thing's continuous everywhere for all real numbers. All right? That's my domain as well as my continuous interval. Now how about this one? I got tangent of x over x squared plus 1. Tangent of x over x squared plus 1. If I'm thinking about this, I'm looking at that x squared plus 1. Again, no problems with that x squared plus 1, right? Because there's no way to make that 0 on the bottom. So that has no issues. But if I think about the tangent for a minute, the tangent is sine over cosine, right? Well, we still can't divide by 0, right? So anywhere where the cosine is 0, I'm going to have a problem, right? And so then I'm looking at my unit circle. Well, where's the cosine 0? Well, pi halves has a cosine of 0. 3 pi halves has a cosine of 0, right? So pi halves, 3 pi halves. I could go around once, plus pi halves, so 5 pi halves, and 7 pi halves, and so on, right? And so we could generalize this as, let's see, I could do So notice I have 1, 3, 5, 7, and so on. And I should say also negative pi halves, right? So these are plus minuses on this, plus minus, plus minus. These are all the problems where I'm going to have a break in my graph, right? Where it's not defined, where it's discontinuous. So if I was to generalize that, I'd make that 2n plus 1 pi over 2, where n is any integer, right? My integers, of course, are let's test that. Like, for example, if n is 0, I'd have 2 times 0 plus 1 pi over 2. See how I get 1 pi over 2? If n is 1, then I get 2 times 1 plus 1, I get 3 pi over 2. If n is 2, I would get 5 pi over 2. If n is 3, I get 7 pi over 2, and so on. If n is negative 1, then I'd get my negative pi over 2. If n is negative 2, then I'd get my negative 3 pi over 2, and so on. Right? So it hits all of these with that one right there. And so how do you say that? You say x such that x is all real numbers except for x cannot be 2n plus 1 pi over 2, where my n is an integer. That's how you say that. All right. And again, it's just taking all those out. Right? Saying everything but. All right, here we got the cosecant. Let's go ahead and write that. We know the cosecant is 1 over sine. So this is the same as 4 over the sine of 4x, right? So we're going to have an issue anytime that is 0, right? Well, that would be a problem. We know the sine, here, let me write this. No, we know the sine of 0 is 0, right? So if 4x equals 0, in other words, divide by 4, divide by, if x is 0, then we'd be dividing by 0 for this function, right? We also know the sine of pi is 0. So if 4x equals pi, in other words, if x is pi fourths, we have a problem as well. All right, and I could keep going with this. I also know the sine of 2 pi is 0. So if 4x equals 2 pi, in other words, x equals 2 pi over 4, or pi halves, I have an issue. Let's generalize this. This is the sine of n pi, n being an integer, right? So if n pi equals 4x, or 4x equals n pi, let me write the other way. 4x equals n pi, where n is an integer. So I have n pi over 4. Again, n is an integer. Then that will make this thing discontinuous, right? So where's this? We're continuous everywhere except, so I say x such that x can be anything, any real number, except for that n pi over 4, where n is an integer. Remember, the integers are -3, -2, -1, 0, 1, 2, ... That's my integers. All right, here we've got a rational function, x minus 3 over x squared minus 9. And so if I'm thinking about my rational functions, just like when I was in pre-calc, I'm thinking, oh, if I have two factors that cancel, remember we have a hole right there. So we have a hole at x equaling 3. All right, we have a hole there because we know x can't be 3, because if I plug 3 into the original, I'm dividing by 0, right? So I know there's a discontinuity there. What kind of discontinuity? Well, if it's just a hole, that's going to be a removable discontinuity, right? So that'll be a removable discontinuity at x equaling 3. That's a hole right there. Now let's finish the rest of this. I'm going to have a vertical asymptote here at x being negative 3, right? So this thing behaves like 1 over x plus 3, right? With that vertical asymptote, it behaves like this, except the problem is I've got a hole. And let me kind of draw this. Yeah, I've got a horizontal asymptote y equals 0 as well. I've got this hole at x being 3. Well, where's the hole at? Well, I can plug it into the simplified form. If I plug 3 in for x, I got 1/6. So at 3, I've got this hole of 1/6 right there, right? So where are my discontinuities? Well, I have two of them. One's a removable one. The other one's that vertical asymptote, right? That also is a discontinuity, but it's a non-removable discontinuity. But both of them are discontinuities. Negative 3 and 3 is where this thing is not defined. So where is f of x continuous at? From negative infinity up to negative 3, and then between negative 3 up until the hole, and then after the hole, it's also continuous after the hole. So this is where it's continuous, this function. Well, like the previous example, we want to go ahead and factor this rational function and see if any factors cancel. Because if a factor cancels, I'm going to have a hole. So it looks like I'll have a minus 5 plus 3. It looks like nothing cancels, so I actually have vertical asymptotes at both of these spots. So at x equaling 5 and x equaling negative 3. X equaling 5, x equaling negative 3. So those will be discontinuities there. I'd have a horizontal asymptote y equals 0. If I was graphing a few, I don't know, I think it's something like this. If I remember right. I haven't plugged any values in, but the point is, those are non-removable. I don't have any removable holes, right? But those are where I'm discontinuous, both being non-removable. So if I was to define, where's this thing continuous? Well, from negative infinity up to negative 3, and then I have a break. I'm continuous between negative 3 and 5, and then I'm continuous after that. Due to our two vertical asymptotes. Well, thanks so much for watching. Continuity. Take notes. See you next time.